Great. Hot out. I live in Huntington Beach,
Yeah.
and it's like 20-degree difference.
Oh yeah. I was
Well,
gonna say probably it's a bit cooler because of the water, but
yeah,
yeah.
it's so nice. And then I got out of my car here. I'm like,
Summer is in full swing right now.
yep,
Yeah, it usually waits until like July before it gets like really, really hot. Like May, June, usually it's still okay. But yeah, July, August, September, it's yeah, this is rough.
yeah.
All right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Pretty good.
Good. Hopefully everyone's staying cool. It's yeah, the heat's really kind of kicking in now. Okay. So today is just gonna be a pure lecture day. So we did ANSYS activity 2 yesterday. We're doing ANSYS activity 3 tomorrow. So kind of a double header this week. I think this is probably the last time we'll have it. I think from here on out we'll have just one ANSYS activity per week. But just today, just this week, just because I want to get all for the first 3 ANSYS activities in before you start working on the midterm project in earnest. That's why we're doing a double header this week. And so, but today we're taking a break. Today we're just doing a lecture. Today's all about meshing, and so we're going to go over the 3 element types, and then we're going to go over some more kind of advanced topics in meshing, kind of some more ANSYS specific stuff that'll probably help you guys out with the activity tomorrow as well as your midterm projects. Okay. Speaking of the midterm projects, I did post that this afternoon, so we will go through that probably after the break. So we might take an early break today, just because 3D element types shouldn't take us too long to get through. So we'll get through that. We'll talk about the midterm project, what that's all about, and then we'll finish the lecture with some more advanced meshing. Okay. All right. So announcements. Remember, ANSYS activity 2 deadline for that's coming up quickly, just because I don't want it to overlap too much with the third activity. So ANSYS activity 2 is due tomorrow night. So please make sure you guys are working on that. We did get through quite a bit of it yesterday together in class, but there was quite a bit for you guys to do on your own as well. And of course, you have to do the write-up as well, which takes a bit of time. So make sure you get that in time. Okay. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay. So yesterday we finished our lecture talking about the 2D element types. So what we saw was, all the options that are available to us in ANSYS in terms of element shape and element order. We saw what those elements look like, what their shape functions look like, and that kind of led into a discussion more about kind of how these different element properties actually affect your finite element solution. Okay. So everything that we talked about yesterday is going to apply to the 3D elements as well. In fact, it kind of helps speed things up with the 3D elements because it's basically everything that we talked about yesterday, just with an added dimension. Okay, but we'll start with that today. Okay, so today we're going to go over the 3D element types. And this is going to be relevant for every other ANSYS activity and project that you're going to do for the rest of class, rest of the session, because everything we're going to do is in 3D. Okay. Okay. But like I just mentioned, basically every single element type that we covered in 2D has an analog in 3D, which has basically the same properties. And so in fact, this lecture and the last one kind of go hand in hand. Okay. So I'm not going to repeat everything that we talked about yesterday with regard to the shape function and solution, convergence and things like that, and the shape functions, all that stuff. And so, more or less today, we're just going to mention all the 3D element types. We'll look at their shape functions. I'll kind of remind you of the main properties that you need to know in order to kind of make good decisions in terms of your ANSYS finite element simulation. And so this should end up being pretty good. Okay. Okay. So if you recall from yesterday, the first element that we looked into was the very simplest element that we could do in 2D, which was the linear triangle. Okay. So the 3D analog for the linear triangle is the linear tetrahedron. Okay, so let's start with that. Okay. So the tetrahedron, like I think I mentioned last week, is essentially a four-sided pyramid. Okay. Right, so the pyramid has four sides and also four corners, and so we can count them out here. Right, so those are our four nodes. Okay. And just like yesterday, we know that the form of the shape function, or I guess more specifically, the number of terms in our shape function matches the number of nodes in our element. And so if our element here has four nodes, that means our shape function will have four terms. Okay. Okay, so the shape function for a linear tetrahedron, which now is going to be a function of x, y, and z, right? So we have the third dimension. We simply just have the constant term plus all the terms that are independently linear in each of the dimensions. Okay, so it looks like this: a0 plus a1x plus a2y plus a3z. All right. So this is about as simple as it can get, right? So the simplest possible 3D finite element is the linear tetrahedron. And you can see it kind of barely satisfies that minimum requirement. And so in 3 dimensions, we have to at least have some way to have solution variation in each of 3 directions. So that's what the A1, A2, A3 terms show, right? And so those are just simple linear terms that vary linearly in X, Y, and Z. But there's no higher order terms from here as well, and there's no cross terms either. And by nature of being the simplest and having the least amount of nodes, it also means that it's the cheapest, right? So the computational cost per element is cheapest for the linear tetrahedron. Okay. So computing the solution for one linear tetrahedron is going to be cheaper than one quadratic tetrahedron or one quadratic hexahedron. Okay. And so even though it's the cheapest, it still has some positive properties, right? So there's still some good reasons to use it. And so just like its 2D counterpart, the linear tetrahedron has what we call the simplex property. Which, to remind you, the simplex property means that it can mesh basically any 3-dimensional geometry very effectively. right? So triangles, both the triangular elements have this property. So both the 2D triangles and the 3D tetrahedrons. Okay. And so what that means is that, it's you can take a linear tetrahedron and you can use it to mesh almost any geometry, and it can do so pretty reliably. Okay. Okay. Most of the time. Okay. It is still possible to get mesh failures with linear tetrahedron, but it is a lot more difficult to do so. Okay. And so generally speaking, if you have a very complex geometry, usually it's not a bad idea to use a tetrahedral element to mesh it, just because you'll have a much better chance of getting a successful mesh from them. Okay. And again, like I mentioned before, that before I've used ANSYS, and I've only really used ANSYS within the context of this class, and so all my previous work, all my previous research, I've always used a linear tetrahedron, and so there's nothing wrong with it. There are ways to get it to work. It's just that you have to kind of be aware of its shortcomings and kind of plan around it. Okay. And so one of the shortcomings, of course, is the fact that its shape function is very simple. So it doesn't have the ability to capture any complex variations in X and Y or Z. And so if you have, fast gradients or maybe multi-dimensional kind of variations within the element, the linear tetrahedron will struggle to capture those effectively. Okay. And so what that means is that if you do want to get an accurate and reliable solution with the linear tetrahedron, you kind of have to refine the mesh and make the elements smaller than you would in any other case. And so you're even more dependent on the size of the element in order to get an accurate and reliable solution. Right? Right. Which, again, is not the worst thing. And so, remember we talked about yesterday that there are two types of refinements that you can do. You can do an H level refinement, which means that you just make the elements smaller, or you can do a P level refinement where you make the elements, a higher order. So you go from linear to quadratic. And so at the end of the day, both those types of refinement are going to add cost. It's just that, there's different limitations in terms of how many elements you can have in your mesh, or maybe sometimes that the software that you're using, maybe you're using a different finite element software other than ANSYS that does where quadratic elements just are not available to you as an option. Okay. But one issue that you'll run into for this class in particular with this particular license of ANSYS is that the student version of ANSYS or the academic version of ANSYS that you're using in the lab has a hard cap in terms of the number of elements that you can actually have, whether those elements be linear or quadratic. And so you're kind of more likely to hit that cap if you use a linear element. Okay. But that's something that's kind of unique to just this class. If you're using finite elements out, in industry, you're probably going to have a commercial license. And so, you can kind of pump in as many elements as you want. Granted that the cost of your simulation still remains somewhat feasible. Okay. Okay. Another thing with linear tetrahedrons as well kind of goes back to kind of the last point that we made yesterday with regards to shear locking. So remember that, for structural mechanics simulations in general, whatever we compute for the deformation depends strongly on the stress. And since the stress is a derivative-based quantity, if you're taking derivatives of a linear element like this, it could lead to shear loss. So something just to be aware of. Okay. So the kind of the summary for a linear tetrahedron element is that you can use them. They're perfectly fine. They're perfectly valid. It's just that your solution accuracy is going to depend very strongly on the element size. Okay. And so it's even more important than ever to use a mesh convergence test for a linear tetrahedron to ensure that you've reached convergence on your mesh. Okay. And we're going to talk about mesh convergence tests today as well, just to kind of illustrate to you what that is and how that's a nice tool. All right, any questions on the linear tetrahedron? Okay.
Yeah, I have a question.
Oh, question, go ahead.
Yeah, so I'm trying to understand how something with basically something that could be good for complex geometry can at the same time, you know, not be so great for complex solution behavior. When we talk about complex solution behavior, are we just kind of like referring to, like, remember how you showed us the graphs of because FEA is just an approximation. Is it kind of just like based on the mathematical equation that we have, it just doesn't approximate it as close,
So
whereas the geometry itself, like the triangle kind of being the shape that it is, and also smaller than a quadrilateral, would kind of be better with the geometry. Like so basically if we had a quadrilateral the same size as a triangle, could we say that it's not as good for the geometry itself, but it is more of it's better at capturing the complex solution behavior?
yeah, so the geometry and the solution are different things. And so when I say that the tetrahedron is better for complex geometries, it means that you're going to be able to mesh it more reliably. Now, granted, I don't think that's something that we've really experienced in the class so far with the ANSYS activities, because ANSYS activity 1 and 2 have been very simple geometries, and so there hasn't really been an issue meshing those. But when you're using finite elements for kind of more practical problems, you're going to have a very complex CAD file. And what you're going to see is that if you try to use a quadrilateral element or a rectangular element, you're going to run into issues with the meshing. And so the meshing is going to give you an error. It's going to say that it can't create a mesh in this situation. And so in those situations where you're even just struggling just to get a mesh, because that itself is not a given. It's usually not a bad idea to start with the linear tetrahedron just to be able to get a mesh. But then when you actually go to solve for the solution, the linear tetrahedron has more restrictions on it, where you have to refine your mesh. You have to make the mesh element small enough to make sure that your finite element solution is reliable and accurate. So that's the distinction I kind of make. So for complex geometries, the challenge with the complex geometry is just even getting a mesh on it without any errors. But then once you do get a mesh, you have to kind of be aware of how small your elements have to be in order for your solution to be accurate and reliable. Does that make more sense?
Yeah.
Okay, good. Okay. All right, so let's move on. So let's talk about the quadratic tetrahedron. Okay. So quadratic tetrahedrons are the 3D analog for the quadratic triangle. Okay. And so just like the quadratic triangle, we're going to start with our tetrahedron element just like this. Okay. Let's label all the corners. Right, and then just like we did in 2 dimensions, we're going to add a mid node in between each of those corner nodes, so along each of the edge space. And that's going to add 4 additional nodes for our shape function. 5, excuse me. 6. Can't count the number of edges. 6, 8, 9, 10. Okay, so we have 10 nodes overall. So that means our shape function will have 10 terms associated with it. Okay. All right, so if you go ahead and write out our shape function, okay, which again is a function of x, y, and z. Okay. So first we start out with all of the contributions from the linear tetrahedron. So that's the constant term and all the terms that are purely linear in x and y. Okay. Then we have the quadratic terms. And so we have a4x squared, a5y squared, a6z squared. Okay. So that adds 3 more terms. And so that gets us up to 7. But we need to add 3 more because we have 10 nodes. Okay. And these last 3 terms here are going to be our cross terms, so products of 2 different variables at the same time. So you have a7xy plus a8xz plus a9yz. Okay, so you can see that, just even making the jump from linear to quadratic here actually makes a pretty big difference. Okay, so we're going from 4 terms in our shape function up to 10, and so that's over 2.5 times the cost. Okay. And so with 2.5 times more terms, that means that you can associate that with 2.5 times more cost. So each quadratic tetrahedron that you use compared to a linear tetrahedron is going to take 2.5 times more computer memory to store the result. It's going to take 2.5 times more time to run the solution. Okay, so it is actually a pretty significant bump. Although, again, because the problems that we're mostly doing in this class are fairly simple, you're not really going to notice the difference between, a 3-second solution versus a 7-second solution. But it is, for more complex cases, that is something to keep in mind. Okay. Now, the nice thing about the quadratic tetrahedron is that it's still a tetrahedron shape, and so we still maintain the simplex property. Okay. Which again means that, if you have a complex geometry that is, you're kind of struggling to mesh it with the hexahedron elements, a tetrahedron will probably have a much easier time doing that. The downside to the quadratic tetrahedron, and this is a downside that's also shared with the linear tetrahedron, is that, even though it has the ability to fill complex spaces effectively, or I should say it reliably, it doesn't do so very efficiently. And so what that means is that, for a given element size, if you're using a quadratic tetrahedron, your mesh element counts will be fairly high. Just because, it takes more tetrahedrons to fill a space than a hexahedron. Which, if you think about it, for a quadratic tetrahedron, if each element for a quadratic tetrahedron is 2.5 times more expensive, and it takes a lot of tetrahedrons just to fill a space, you're looking at a pretty, the cost can get away from you pretty quickly, and so just kind of something to be aware. Okay. But on a per element basis, we do get better solution properties just because we do have those quadratic terms. Okay. And so if your solution is changing more rapidly than a linear term, then we can capture that with the quadratic. And the addition of those cross terms, A7, A8, and A9, any type of solution behavior that depends on multiple variables changing at once. So, A7 is X, Y, A8 is X and Z, okay? A9 is Y and Z. The quadratic tetrahedron will be able to capture that more effectively. Okay, but besides that, not much else to say. And so, we kind of talked ad nauseum yesterday about the differences between linear and quadratics. And so, a lot of that same discussion applies here as well. All right, any questions on the quadratic tetrahedron? Okay, all right, so next, let's go to the rectangular elements. So we'll start with the linear one first. So a linear rectangular element in 3 dimensions is known as a hexahedron. It's also sometimes called a brick. Sometimes people call it a brick, and it's kind of fun because it is a brick. But it's so different than hexahedron. It sounds a lot more casual. Okay? So our typical hexahedron element looks like this, and so it's just a box. I remember when I was like in 4th grade or something, and I drew my first 3-dimensional box, and it blew my mind that I could draw something in 3D. So, but as I've aged, I've gotten worse at it, and so that's why that back corner kind of looks kind of weird. Okay, so remember for the linear elements, we're only counting the corner nodes. Okay. So there are 8 of them here. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And so with 8 nodes, then our shape function is also going to have 8 terms. Okay. Let me write it underneath it just because I think otherwise it might be squished up there. Okay, so our shape function looks like the following. And so, remember that for a linear hexahedron, we are only, our shape function could only have linear terms, okay? And so we may have pseudo-linear terms. In fact, we definitely will, but there are going to be no quadratic terms, so no x squared, y squared, or z squared. Okay, so we start with the pure linear terms. And so we have a0 plus a1x plus a2y plus a3z. Okay. Okay, and so compared to the quadratic tetrahedron, so we're going to skip x squared, y squared, z squared. We're just going to jump straight to the cross terms because those are pseudo-linear. Okay, so we have a4 here, xy, plus a5, xz, plus a6, yz. Okay. So that gets us up to 7 terms. Okay. And you may be wondering what the 8th term is because we've run out of pairs. The 8th term is actually the triplet, and so it actually is all 3 of those terms, all 3 of those variables together. So it's a7, x, y, z. Okay. Which technically is cubic order because we are multiplying 3 variables together. But individually in X, Y, and Z, that term there is linear. So we call that the last pseudo linear term. Okay. So the linear hexahedron kind of shares all the pros and cons with the linear quadrilateral that we talked about yesterday. Okay. And so on the one hand, our shape function here has a lot of nice terms in it, right? And so for being a linear element, we do get a lot of these kind of more higher order cross terms, right? So any products between two variables. So that's a nice benefit, of course. So the fact that our shape function has quite a few terms means that we can capture a lot of good solution behaviors. The other nice thing about rectangular elements is that they do fill the space very efficiently, right? It may not work every single time, but for the cases where we can get a mesh, we can produce a mesh with less elements overall compared to a tetrahedron. Okay. Another nice benefit to the rectangular elements, and I don't think we mentioned this yesterday, actually, I might have forgotten to mention it, is that, part of the reason why that hexahedrons or bricks can fill space more effectively is that they are more robust against skewed elements. And so you can have a rectangular element that looks very skew, and it doesn't have as negative an effect on your solution. Okay. So just to kind of refresh your memory, when I refer to a skewed element, looks something like this. Maybe we have a very thin and slender hexahedron element that looks something like that, okay? Which is much longer than it is wide. And so, if you remember from last week, we brought up this idea of mesh quality, where generally speaking, you want your elements to be as equilateral as possible. So all the sides and all the interior angles are roughly the same, okay? That is still true for hexahedron elements. Hexahedrons do still like to be more kind of equal and square in shape. But, if you do have to kind of stretch and kind of distort your elements, hexahedrons or the rectangular elements can deal with that a bit better. Okay. And actually, once we get to the second half of class today, we're going to bring up the idea or the concept of mesh quality again, and we'll talk about kind of more specifically about why that's a bad thing. You want to avoid this. But generally speaking, hexahedrons, they can handle more skewed and kind of smaller or larger aspect ratio elements than the tetrahedrons. Okay. Okay, but of course the downside to hexahedron elements is that it is more difficult to get a mesh, right? So you're more likely to get a failed mesh if you try to force hexahedrons. Okay. And that, of course, is because hexahedrons do not have the simplex property. So again, probably not for the ANSYS activities. Pretty much all the activities that we're going to do in class are all fairly simple, just because they're kind of designed that way, just as a way to kind of introduce the software to you and kind of give you a first look. But when you're working on the midterm project, when you're working on your final project, you're much more likely to get meshing errors. Okay. And that's more likely to occur with hexahedron elements. Okay. Okay, that is the linear hex. Our question from the chat. So is there a way of prioritizing between different element types and between linear and quadratic? Should we start with one of those shapes and see where it works and goes from there? Yeah, no, it's a good question. And so, I would say, if the meshing is not that expensive in the fact that, you can get a mesh within, like a minute or two, which, for everything that we're going to do in this class falls into that category. I'd say there's no harm in trying to get a complex mesh on that. And so using hexahedron elements, using quadratic elements, and just kind of see where it takes you. Okay. Because worst case, if the meshing does fail, you'll find out, within 30 seconds. It gets a bit more complicated when you are meshing more complex geometries and you're going to be required to get meshes in the millions or even tens of millions. Because then in those situations, the meshing can take quite a while. It can take up to a couple hours. And it's one of those things where, meshing is actually a pretty computationally intensive process. And so for certain geometries, it can kind of lock you up from doing anything else on your computer. So for this class, I would say just try just try to get a hexahedron quadratic mesh, kind of see where that takes you. But just know that for more complicated cases, you kind of have to be a little more careful beforehand, just because the meshing can be a bit more complicated and more expensive to do. Yeah. Yeah, you start to get a feel for it too, kind of once you start to mesh it quite a bit. Like I know, like for a lot of the work that I do a lot of simulations on these biological geometries, which are, I work on with CAD files of people's blood vessels, which are very strange, kind of not standard geometries at all. And so I knew that even if I had a hexahedron mesh available to me, I knew it would be very difficult to get a mesh on those situations, just because the geometries are just so kind of unique and kind of strange. And so I just kind of go for tetrahedron right away, and I just rely on the mesh refinement in order to get the accuracy that I need. Yeah, yeah. I think that's the other thing to remember too, is that regardless of which element that you choose, and all the elements that we've gone over so far, they're all perfectly valid. They're all perfectly fine, and so you can get a reliable solution for any of the elements. It's just that it's more about knowing the limitations of these types of elements and how to use them to the best of their ability to get a reliable solution, because that's the goal at the end of the day. All right, any other questions on the linear hexahedron? Okay, good. Okay, and then so let's finally go through the last element type here, which is the quadratic hexahedron. So this one's always fun. Okay. So just like we did with the tetrahedron, we're going to do the same exercise here. So we're going to draw our brick element or our hexahedron. All right, so let's draw all our corner nodes. We'll get all 8 of those first. Okay. And then we're going to add a mid node in the middle of each of the edges here in this element. And there's 12 mid nodes here, so there's going to be quite a bit to show here. I think I got every single one. Okay. So let's see, we have 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, good. And again, you don't have to have the numbers in the same place as me. It's for our discussion here, it doesn't really matter. Just make sure you have 20 of them. Okay. All right, and so of course with 20 terms that are 20 nodes, that means our shape function will also have 20 terms associated with it. Okay, so let's just go ahead and start. So I'm gonna go ahead and write them kind of in batches just to kind of illustrate kind of the different groups of the terms in the shape function. So we have A0 plus A1x plus A2y plus A3z. Okay. All right, so those are all the basic linear terms, right? And so that's kind of the baseline, that's our starting point. Okay. Next, let's add the cross terms. The linear cross terms, and so we have A4 xy plus A5 xz plus A6 yz. Right, let's throw in the triplet here as well, just because we're gonna need it. Okay. So those are all our pseudo-linear terms, and so those are all of the possible terms that have x, y, and z to the raised to the first power. Okay. Now we're going up to the quadratic terms. Okay, first we have the straight up quadratic term, so x squared, y squared, z squared. So you have A8 x squared plus A9 y squared plus A10 z squared. Okay. Good. All right, and so now we need to start adding the quadratic cross terms. And so terms that have x squared, y squared, or z squared, but combined with another variable. Okay, so then we have A11, let's do x squared y plus A12 x squared z plus A13 xy squared plus A14 y squared z. Okay. Plus A15 x z squared plus A16 y z squared. All right, 17 terms, and we're not even done just yet. Okay. All right, because so now that we have all of the doublet terms, and so all of the terms with two variables with the quadratic, now we have the quadratic triplet terms. Okay, so terms that have all three x, y, and z, but one of them is going to be squared. A17 x squared yz plus A18 x y squared z. And finally, A19 x, y, z squared. Okay. So writing the shape function for the quadratic hexahedron takes up an entire page. Okay. But we get a lot of really nice behavior here, right? So a lot of quadratic terms, a lot of kind of combinations of terms. Combinations of x, y, and z. And so, this is going to cover a very wide range of solution behavior. Okay. And once we get to the second half of the class, we'll talk a bit more about why that's, we talked about it a bit yesterday, but, we're going to talk about another factor to consider about why having these extra terms are worth it, especially the quadratic terms. Okay. Because when you compare a quadratic term to, the behavior of a quadratic term compared to the behavior of a linear term, the quadratic term has certain advantages that we take advantage of in our solutions. Okay. Okay. But besides that, there's not much too else to say, right? So this is kind of just the culmination of kind of everything that we've discussed. And so if you compare this to the linear hexahedron, there are pros and cons with this. This is 2.5 times the cost. Okay. The linear hexahedron only had 8 terms. This one has 20. And so that's a 2.5 times increase, just like going from linear tet to a quadratic tet. All right, any questions on the quadratic hexahedron? Okay, good. Okay, so before we kind of end our discussion here, I do want to make kind of a quick table, okay? Because we've covered, kind of 2 dimensions of element decision making. Okay, you can either you can choose, or you have to make a decision in terms of the element shape, and you have to make a decision in terms of the element order. Okay, so I have this kind of nice handy table, which just kind of summarizes everything that we've kind of talked about in terms of their properties. Where, if you do have to make a decision, this table can kind of help you kind of choose which one makes the most sense for your situation. Okay. All right. So remember, so the first dimension that we can choose is the order. Right. So you can either choose linear or quadratic elements. And so there are pros and cons to both of these. And so we're going to make this into basically a table. Okay. And then in addition to the element order, we can choose the shape. Okay, so that'll be kind of our other dimension there. Okay. So I'm going to group the triangles in 2D and the tetrahedrons in 3D. Just because they kind of have the same properties. Okay. And then we'll see if I make this table, good enough here, or if we need more space. And then the other type of element shape that we looked at was the rectangular one. So these are the quadrilaterals / hexahedrons. Okay, so we're going to go through, the pros and cons of each combination because, you essentially have 4 different options that you can choose from. Okay. Okay, so let's start in the top left, and so that is the simplest element that you can do. Okay, so the linear triangle with the linear tet. Okay. So on the positive side, okay, probably the biggest positive to using a triangle or tetrahedron is that simplex property. Okay. Which again means that it can mesh almost any geometry pretty reliably. Okay. Which, I know I've said this a lot, but that is a very, very valuable property to have. Just knowing that you can get a mesh on a geometry is golden sometimes. Okay. I think a lot of typically for this class, a lot of you kind of really experience it on the final project, when you kind of you're using ANSYS to try to mesh any of all the kind of crazy projects that you guys are working. Okay, but of course the downside to the tetrahedron, and so this actually goes for both the linear and the quadratic, is that it does not fill space effectively. Okay. And so for a lot of times, if you do get a mesh, it's going to have a pretty high element count. Okay. which can drive up the cost, but more effective or more, I guess, immediately relevant for this class is that you may run up to the element limit for your particular ANSYS license. Okay. Okay, another downside for the linear TET is that you do have to look out for shear locking. So you have to make sure that you refine your elements enough to avoid shear locking from occurring. But on the bright side, if you're doing a simulation that doesn't involve structures, and so let's say you're running a thermal simulation or a fluid simulation, I believe it's true for electromagnetics as well, but I'm not as familiar with the nuances with electromagnetism just because haven't run those simulations too much. Okay. And so if you're running a simulation that does not involve structures, linear TETs are actually a great option because each of the elements themselves are cheap. And the linear nature doesn't compromise your solution nearly as much as the structures. In fact, I can tell you kind of more specifically for fluids, right? In fluids, there's kind of another unique thing that happens, and this is just trivia. So this is not something that I'm not going to write it down because it's not something I expect you to remember. But in fluid, when you're solving the fluids equations, when you're trying to solve Navier-Stokes with finite elements, there's kind of a separate issue that occurs, which has to do with we call it stabilization. And so because fluids are convection dominated, what that basically means that there's flow, right? Because of the way finite elements kind of discretizes Navier-Stokes, you could have solutions that kind of oscillate and kind of have these vibrations that are not necessarily physical. And so you have to add some additional terms or some additional stabilization terms for finite element fluids. And that stabilization only works for linear elements. Okay. I think there's research going on right now to come up with stabilization schemes for quadratic elements, but it is pretty challenging. And so I think it only really exists for very niche, kind of very simplified problems. And so I would say the vast majority of fluid solvers that use finite elements utilize linear elements just because of that stabilization scheme. Okay. So that's kind of just a bit of more specialized information for that. And of course, the last positive is that each element itself is very cheap. And so each element only has 4 nodes. Okay. And which of course, if you compare that to the most complex element, the quadratic hexahedron, which had 20 nodes per element, having 4 per element is pretty cheap. That's 5 times as cheap. Okay, so those are the pros and cons for the linear TET. Okay, so let's go ahead and move on to the quadratic TET. So some of these are going to move over as well. Okay, so the quadratic TET also has a simplex property. Okay, and so you can mesh pretty much any geometry with the quadratic TET. Okay. You do still have the issue of space filling, right? And so you're going to end up with pretty high element counts if you have a quadratic TET, same as a linear TET, because that property is a function of the shape of the element itself, not necessarily its order. Okay. Okay, so the first 2 points just kind of carry over. I'm not going to write them down again. The nice thing about quadratic elements is that you generally don't have to worry about shear locking. Right? Another positive is that because it's quadratic and because you don't have shear locking, it works great for structural simulations. Okay. It should work pretty well for thermal as well. The heat equation is not that difficult of an equation to solve. For fluids, I don't know too many solvers that use quadratic elements for fluids, just because of the stabilization kind of issues that I just kind of alluded to. I'm sure they exist out there, but and actually, if ANSYS kind of gives you that option, I'm sure ANSYS has a stabilization scheme. They just probably aren't sharing it with the world. They're just kind of keeping that a company secret. But in theory, it should work it should work well for fluid and thermal as well. Okay. And of course, the downside with quadratic elements is that on a per element basis, they are more expensive. And so remember, when we compared the quadratic TET with the linear TET, it had 2.5 times more elements, or 2.5 more times more nodes. Okay, so we have 10 nodes per element for the quadratic TET. Okay, so that's all the pros and cons for the triangular elements. Okay, linear and quadratic. Let's go ahead and look at the rectangular elements now. Okay. So first thing to note with the rectangular elements, and probably the thing that most people experience at one point when trying to use these, is it is difficult to mesh complex geometry, or your mesh is more likely to fail. Okay. So what's going to happen in those situations that you're going to try to create a mesh using a rectangular element, and ANSYS is just going to give you an error that says that you can't do that, and you're going to be wondering why. And so in those cases, you could switch to a TET, or one thing you could also do is that if you could identify where or which regions in your geometry that are having trouble meshing with hexahedrons, you can convert just that section to tetrahedrons and try to maintain hexahedrons for everything else. Okay, so you're taking a mixed meshing approach, which is what we're going to do tomorrow in activity. Okay. All right, but on the bright side, for the hexahedron elements, they are very efficient at filling space. And so for the cases where it does work, you're not going to run up the element count too much. Okay. Okay. Other things to keep in mind is that a linear hexahedron is great for basically all types of equations, so thermal, fluids, and structures. And then the other benefit, of course, is that per element, there's only 8 nodes. Okay, which is still relatively cheap, right? So only 8 nodes is still, I would say on the cheaper side. Okay. And among those 8 nodes, or among the 8 terms in our shape function, we do actually get some nice terms, some nice combinations of x and y. And so, we can still capture some interesting solution behavior with those 8 terms. Okay. So, so it's a pretty good balance of cost and solution problems. Okay. And then finally, we have the quadratic hex. And so we'll go ahead and finish up this table, and then we'll take an early break just so we can talk about the midterm project right now. Okay, so the quadratic hex still has the same issue as the linear hex, right? And so if you have a complex geometry, it can still be difficult to mesh it, right? You're more likely to run into errors. But for cases when it does, you are able to mesh, right? It does fill the space pretty efficiently. So your element counts still remain fairly modest, okay? It's great for all of those types of equations as well. Okay. The main difference between the linear and quadratic hexahedron is the nature of the shape functions and the cost that it takes to get them. Okay. So the downside, the most immediate downside, is that your quadratic hexahedrons are the most expensive element. Okay, so we have 20 nodes per element, and so that is not cheap. Okay. But the bright side is that, among those 20 nodes, we are able to capture, a very wide variety of different types of solution variation. Basically, any combination of X, Y, and Z, the quadratic hexahedron has it covered. Okay. Okay. So solution coverage is important because it's that means that we're going to be able to get an accurate solution without nearly as many elements. And so, even though the quadratic hex per element is more expensive, we can probably reach a converged accurate solution, without a high element count. Okay. Any questions on this table here? Okay, all right, so let's take an early break. And so when we come back from the break, so we'll come back at the break, let's come back 4:10. Just because I want to talk about the midterm project. So we'll talk about that for maybe 20 minutes, and then we'll move on to the second half of the lecture, which is advanced meshing. Okay, so we'll come back in about, I guess, 9 minutes from now. Okay, it's 4:10, so I know today pretty short break, but I did want to have time to talk about your midterm project. Okay, all right. So I just posted this afternoon, and so you can feel free to start working on it now. Although in a traditional semester, I typically don't present this until after we do ANSYS Activity 3. Just because ANSYS Activity 3, I would consider that to be kind of the last of the basic ANSYS tutorials that we're going to do together. Although, in terms of new features and new capabilities, and Activity 3 doesn't introduce too much. And so, I think it's fine to kind of introduce this now. I think the only thing you're missing with Activity 3 is just some additional practice with ANSYS. Okay. But we are doing Activity 3 tomorrow. And so, feel free to start this project after that. But the due date is, with everything in the summer, everything just comes up so quickly. But the due date is going to be Sunday, July 19th. And so that's not this Sunday, that's the following Sunday. So, I want to give you at least more than a week to work on this. So that's kind of why I'm presenting it to you today. Okay. Okay. Anyway. All right. So the whole idea with the midterm project is for you to do a full, or what I consider to be a full finite element analysis on a part. Okay. And so that not only includes, doing the simulations, which we've been doing, but also preparing a report. Okay. And the report is going to be in the style of a formal kind of technical report that you would submit to kind of publish your findings or report on your findings from a finite element simulation. Okay. Okay, and so you're going to be applying basically everything that we've learned about ANSYS so far. So meshing, boundary conditions, material properties, and you're going to be doing it all on your own. Okay. So the other big difference is that, for all the activities that we've done so far, I've kind of, walked you through kind of everything, just to kind of make sure that we all kind of get the same result, and also just because it's a teaching opportunity. Okay. For the midterm project, I'm only going to be providing you with the geometries, and it's going to be up to you to determine, how you're going to mesh it, what materials you're going to choose for it, what your boundary condition is going to be, and then to write the report all on your own. Okay. Okay. All right. And so the first thing you're going to have to do with the midterm project is you're going to have to choose your geometry. Okay. So I'm giving you 3 options. Okay. You only have to choose one of them. Okay. You can do more than one, but I'm only going to grade one. So choose the one that you think will be the best for you. Okay. So option 1 is this geometry, which I call the bearing housing. And so it's this kind of device right here. You can kind of see it's meant to have a kind of a rod that kind of goes to the middle. There's probably some kind of ball bearing. There's probably some ball bearings in here that's going to cause the rod to rotate. But we're just looking at just the fixture. Okay. The second option for geometry is a piston rod, and so it is a geometry that looks something like this. So you can see that it probably attaches to something here. This is probably which attaches to a piston up here. Okay. And the last geometry here is a pressure tank. And so it is a cylindrical pressure tank. And so it's designed to have some kind of fluid running through it. And so you're probably gonna have some hydrostatic pressures being applied on this tank here. You can apply some forces from the outside as well. Okay. And so those are your 3 options. And so you need to choose one for your project. Okay. Okay. And then once you've chosen your geometry, that's when you start to think about, what are the materials, what are the meshing, what are the boundary conditions that you're going to do. Okay, so let's talk a bit more about the requirements for the project. Okay, so the first requirement for your project is going to be some kind of objective. Okay, now we haven't really talked about this, so this will be kind of the first time that this idea or this concept of an objective is kind of introduced to you. Okay, but in practice, as cheap and as easy as a finite element simulation is to perform, right? And so, if you compare, again, if you compare it to an experimental setup, right? A finite element simulation is very cheap because you're just essentially just clicking buttons in a computer. But even then, it still has a cost. The main cost being time. Okay. And so there's never a situation in reality where you're just running a finite element simulation just for the heck of it. Okay. There's usually some kind of engineering question, or there's some kind of engineering objective, some kind of analysis that you want to do or to get answers for that the finite element simulation is can help you with. Okay. Okay, so I want you guys to come up with an objective to for your project. Okay, so you're gonna have to do a little bit of storytelling here. So basically, once you've chosen your geometry, think about what are some common engineering situations that this geometry would be subjected to, and then think of an objective that you can do or that you can answer using a finite element simulation. Okay. So to give you an example, right? So if you think back to yesterday with ANSYS activity 2, we had an objective for that simulation. And so the objective for that simulation is to determine, right? So we had our bike crank, and our question was that, if we apply 100 pounds force in bending on this bike crank, is it going to fail, or is it still going to be within its factor of safety? And we used the finite element simulation to determine whether that was the case or not. Okay. So think of something like that. Okay, so I'm not going to give you, too many hints with these geometries here, just because I want you guys to think of your own objective. But that's the first thing that you have to think about. Okay, you can think of it almost like a hypothesis, right? So if you're running a typical laboratory experiment, right, the first thing that you do is you come up with a hypothesis to determine, the question or the scientific theory that you're trying to test or verify with the experiment, and then you run the experiment, you get your data to test whether your hypothesis was true or not. Okay. And so, you should think about your finite element study in the same way. And so instead of conducting a physical test, instead you're running a simulation. And then based on the results and based on the data that you get from the simulation, you can then use that to either answer your original objective or not. Okay. Okay, and so some questions that you can answer here. And so are you interested in the mechanical stress and the critical area of your geometry? Are you testing for failure? Are you doing a stress analysis, a factor of safety analysis? Okay. Well, are you interested in seeing whether your part's going to fail under typical loading scenarios? What's the maximum deflection or deformation? Are you trying to minimize costs by maybe by choosing maybe a different material? Maybe you're looking to optimize the design, change the dimensions a bit. Okay. Maybe think of design criteria. Okay. Okay. And so, kind of the main thing that you should think about is that your objective should define what you're looking for in your finite element analysis. Okay. And you need to make that very clear in your reports, and everything that you're going to do in terms of your results are going to be in support of that original objective. Okay. So take some time, and if you're having a hard time thinking about an objective for your geometry, definitely talk to me, and we can kind of brainstorm something out. Okay, because again, the point of a finite element simulation is not just simply to produce some pretty looking plots. It's to take the results from those plots and actually do something useful with that, and that's exactly what the project objective is going to be. Okay. Now, this midterm project, it is going to be a bit different than the final project because, I'm providing you the geometry. So you kind of have to come up with a story or you have to come up with an objective that fits one of these geometries here. Okay, so that can be a little bit challenging. I'll give you kind of a preview of your final project. So for your final project is going to be very similar to the midterm project. The only difference is that you're going to be able to choose your own geometry. And in those situations, it's much easier to come up with an objective because I would say probably over half, maybe like 2/3 of the class, typically they use the final project as an opportunity to analyze something that's related to their senior design project. And so, maybe if you're on a legacy team, maybe you're thinking about, redesigning a certain part or remanufacturing a certain part. You want to run an FEA to determine whether that's feasible or not. And so that's a bit easier to come up with an objective. But for this midterm project, you have to come up with an objective for one of the geometries that I give you. Okay. All right. Any questions on the project objective in terms of what's expected for that? Okay, good. Okay. Next thing that you're going to the next requirement for the project is your finite element modeling and methodology decisions. Okay. So in producing a finite element simulation on this geometry, you're going to be making a lot of modeling decisions along the way. Okay. So very basic things like, what material are you going to use? What are its material properties? What kinds of elements are you going to use? What are the element size? What's the element order, element shape? Okay. How many elements are going to be in the mesh? Are you going to add any refinement? boundary conditions. And so, we haven't talked too much about boundary conditions, but boundary conditions are going to be a big part of this project as well. So what kinds of loads and what kinds of constraints you're going to put on your model, okay? Do the boundary conditions make sense relative to your original objective, okay? And so, when you are basically writing a report like this, you should write it from a perspective that you're trying to justify all of your decisions, okay? There's a saying that's commonly said in the world of computational engineering is that when you do a simulation, nobody believes your results except for you. And so it's kind of up to you to kind of justify to your readers that you've done all the necessary steps, you've made all these decisions in a way to ensure that your results are going to be reliable. Okay, so you should come in from the perspective that the person reading your report is coming from a place where they're going to think that everything you're doing is bullshit, right? And so you need to justify your decisions and provide reasoning for everything that you do. Okay, and that's what's going to convince the readers to trust your results. Okay. And so, a lot of your grade, you're going to see from the rubric soon, a big portion of your grade is going to be determined by, how you choose to do the meshing and boundary conditions and the material properties. Okay. Not only that you made the right decisions, but in terms of how you justify them. Okay. I would say that the most common way that I typically mark people down on their projects is that, maybe they make the right decision in terms of the meshing size and the meshing order and the meshing shape and the boundary conditions, the material properties, all that may sound very fine. They may be very sound to me, but the justification usually is something that's typically lacking. Okay. And so I do expect you guys to kind of explain that in detail. If you're not sure how much detail to include, err on the side of providing more detail. Okay. Because that's essentially what I'm going to be looking for. Okay. And so basically through all the lectures that we're having so far, you're going to incorporate kind of everything, just because, if you kind of look at all the lectures we've had, I've been kind of providing you guys with information about how to kind of make these decisions and kind of justify that, to potential readers. Okay. Okay. And so with regards to the boundary conditions, I do have a bit more to say about that. Okay. So part of the requirements for your midterm project is to simulate 3 different scenarios. Okay. So you're not just going to simulate just one combination of boundary conditions. You have to come up with 3 different situations or scenarios to simulate for your report. So again, think of activity 2, right? So the primary kind of scenario, the primary kind of situation that we were looking at was that we looked at our bike crank in bending, right? But in addition to that, we also looked at the situation where maybe the force was applied in compression, and we see how that changed our results, okay? So that's an example of 2 different boundary condition scenarios or boundary condition configurations to run your simulations with, okay? For your midterm project, you have to come up with 3, okay? But, for the midterm project, I am going to let you change one of the material properties and have that count as a different scenario, okay? So, for example, right? A good, 3 different scenarios you can do the following, okay? So in scenario 1, you can use structural steel for the material properties, a single fixed support, and a single tensile load, okay? Right, so I would consider that to be one scenario or one kind of configuration of the boundary conditions and the material properties, okay? Scenario 2, maybe you keep the material property the same, but you change the boundary conditions, you change the loading bit, okay? And so instead of a single tensile load, instead you have 2 compressive loads, and they're going to be applied at a different part or different part on location on your geometry, okay? And then maybe for scenario 3, maybe you use the same boundary conditions as scenario 2, but you change the material properties to plastic, okay? Okay, so that's kind of what I mean by 3 different scenarios. Okay. All right, question. So are we able to change the geometry of the CAD models? You can do that. And so if you want to kind of make a modification to the CAD model, so let's say that, maybe you change the diameter of this hole right here, you can do that. I think the only one you can actually really modify might be the piston rod, because I think that's the only one that's within the ANSYS kind of format for that you can open it up in Design Modeler. I think the bearing housing and the tank are. I think the bearing housing is a parasolid file. I think the tank is an STP file. And so if you're able to load that into SolidWorks and make modifications to the geometry, you can do that as well. Although that's going to be a little bit extra work, I guess you can say, compared to just changing the boundary conditions, changing the material properties. But yeah, absolutely, you can do that as well. Okay. But among your 3 different scenarios here, you can't just pick 3 different materials. I think that would be kind of the easiest way to do it. So I want you to come up with at least 2 different boundary condition configurations. Right? So that can be your scenario 1, scenario 2. But your third scenario, you can just change the material properties for that. Okay. Okay. All right. So a little bit confusing. So 3 scenarios overall, at least 2 different boundary condition configurations, and you can have up to 2 different material properties as well. Okay, any questions on the boundary condition configurations and what's required for that? Okay, good. Okay, so all of that has to do with the setup for your finite element simulation. Okay, and so the next step, of course, is to run the simulation themselves. Okay, and so you're going to be required to present the results of your ANSYS simulations, and so that is similar to our ANSYS activities, and so you're going to be showing screenshots from the ANSYS software. Okay, and so one thing to remember is that generally speaking, it's a good idea to include the total deformation and the equivalent stress for every single boundary condition configuration or scenario that you have. Okay, but also keep in mind that every figure, every result figure that you present should be able to support or present data that supports the original objective of your analysis. Okay. Okay, and so what that means basically is that you're not just going to be just dropping in just figures of deformation and stress into your report. Okay, because if someone that's outside of this class were to look at that, they may not know exactly what to look at. Okay. And so in addition to putting the figures, you also have to explain in the text what those figures are showing. Okay. And so, it's not just showing the screenshots, you have to kind of explain what you're kind of looking at. Okay. And even more importantly, you also need to explain what aspects of these figures, so what aspects of the deformation, what aspects of the equivalent stress, what aspects of those is going to relate back to your original objective. Okay. So for example, right, if you think of activity 2, right, activity 2, we were interested in stress analysis. We were interested in comparing or finding out whether our bike crank was going to fail under the conditions that we gave, right? And so one way to kind of express that, one way to kind of explain that is to show the plot or show the figure of the equivalent stress, and then explain in the text that said, from the results of the equivalent stress, we found that the maximum stress in the crank was found to be X. It occurs at location Y, and therefore, based on these results, we can conclude that the bike crank will or will not fail under these situations. Okay. So that's just kind of a very concise way to do it, but in your report, you're going to talk about it in more detail, of course. Okay. And so besides the total deformation and the equivalent stress, if you feel that there are other screenshots or other results that you can present that support your original project objective, feel free to add those. And so you're not just limited to these. Okay. Maybe it's as simple as just kind of zooming in on a particular region of your geometry to kind of show kind of the stress in a particular region or the deformation in a particular region. That's fine as well. Okay. Or you can include other plots as well. So maybe you include a plot of the normal stress, or maybe you include a plot of the strain. You can also do factor of safety. And so, we'll, I actually forgot to do that yesterday, but you can actually show a plot of factor of safety in ANSYS as well and show that too. Okay. Okay. And then in addition to showing your results, you also have to answer some discussion questions, okay? And so these have to do with, first of all, how do your ANSYS results support or not support the original objective? And so I want you to go through each of the scenarios and explain how the simulation results relate back to the original objective, okay? I want you to talk about any challenges or limitations that you encountered during the simulations. Maybe you had a hard time meshing. Maybe you had a hard time coming up with different boundary condition scenarios. Okay. And then third, just kind of for fun, if you had more time and resources, which, for the summer session, time comes at a premium. And so, if you had more time to do this project, how would you do things differently? Okay. And then finally, the last section of your report is going to be the conclusion. And so just, for the conclusion should be pretty short. And so you're just going to state some very basic closing remarks. And so, just kind of summarize your results and just, any additional things that you wanted to do. Okay. All right. Any questions on this so far? Okay, good. All right. So some final notes here. So I did provide you guys with a template, and so we'll go over that in a second. And so please use the template for your reports. Okay. You don't have to. So the template I gave you is in the format of Microsoft Word. You don't have to use MS Word, but I do at least want you to follow the same sections. Okay. So I want you to have an introduction, a methodology section, results section, discussion, and conclusion. Okay. So please follow that. Okay. There's no page limit. And there's no page expectation too. And so, I've given ACE reports that are, 7, 8 pages long just because they do a great job of communicating the results. It's very clean. I've also given very bad grades to reports that are like, 30, 40 pages long just because they just have a lot of fluff. Okay. And so there's no requirement on the pages. I would rather you guys just kind of focus on just the requirements and make sure you answer all the questions and have all the required information. Okay. So I'm grading you guys based on content and in terms of how thoroughly you kind of answer those. But if you want an estimation, just because everyone always asks, generally these reports end up in the ballpark. Most people end up in the ballpark of 12 to 15 pages. And that includes all the figures that you're going to include as well. Okay. But this is not a requirement. So, don't feel like you have to reach 12 pages or don't feel like, you're limited to 15 pages. That's just where most people kind of end up being for their report. Okay. But again, so you write more or less, it's not going to be kind of this. Okay. I'm also providing you with a rubric, and so we'll go over that in a second as well. So you can refer to that to see how the different sections are going to be graded and how they are going to be weighted. Okay. Teams, there are no teams, and so this is an individual project, so everyone has to do their own simulations and write their own report. Okay. With that said, this is going to be the first time where I kind of, we're kind of going hands off, and so I'm not going to be really helping you guys with the meshing or the boundary conditions. And so definitely feel free to bounce ideas off your classmates, kind of talk maybe about some issues that you're having. Maybe you're having problems with the mesh, and so maybe a classmate can help with that. So feel free to do that, but don't. I am going to be checking, and I have a very good memory. And so if I read reports where you have the exact same boundary condition scenarios as someone else, that's very suspicious to me. Okay. And so make sure you're coming up with your own kind of ideas for the project. Okay. And so last remarks, so don't hesitate to reach out. And so, even though, for the most part, you guys are doing this analysis on your own, I'm not leaving you guys in a ditch, right? And so I'm open to answering questions about anything for the project. The only difference is I'm not going to walk you through all the decisions like we have done with the activities. Okay. Okay. All right, and so that document is here for you to view. Okay, so please make sure you download that document. Make sure you're reading it carefully as you are doing your project. Okay. Let's look at the report template. Okay. Okay, so this is the template for the report. So this template here is a very basic template for kind of a scientific kind of report. And so you have a title, you have your you put your name. So you are the only author here. Okay. And you are part of the mechanical engineering department at Cal State Fullerton. Okay. Okay. And here I have all the different sections that I would expect on the report. Okay. Okay. So first is an abstract. And so, maybe maybe in your lab classes, you've written abstracts before, but an abstract is a very, very brief summary of the entire report. Okay. It's different than the introduction. I think some people confuse the introduction and abstract. The abstract is, if you were to kind of look at your project just from a glance, right? And so if you were to just provide a 100 to 150 word summary of just everything, so that includes your introduction, your methods, and your results, this is kind of what you would do for the abstract. Okay. Okay. And so that's different from the introduction. So the introduction should describe all the background information about your objective. And so this is kind of where you describe your objective as well. Okay. And so you may include a figure of the part to kind of help with the introduction, but the introduction shouldn't be too long. Okay, so the main point of the introduction, it should clearly motivate and describe the objective of your study. And so I should come away with your introduction knowing kind of what you're trying to achieve with your finite element analysis, and that should make kind of sense. Okay? Okay, next we have different sections for your methodology. And so we have a section for your material properties, for your meshing and the boundary conditions. And so this is where you're going to describe the decisions that you made as well as your justification for all of these different decisions. Okay. Next, we have all the results. And so we have the results for each of the three configurations here. Okay. Next, we have the discussion. And so these are the discussion questions that we just went over. So make sure you answer those here. Okay. As well as any additional analysis or discussion of the results, you can, of course, talk about that here as well. And then we have your conclusions. Right. And so remember, conclusion is pretty brief. Okay. References. I don't think you'll have any references for this project just because it's, I'm writing most of that for you. But for your final project, you might have a reference in terms of, maybe where you obtain your geometry or maybe just some reference readings, right? But for the midterm project, you could just delete this section. I don't think you'll have any references. Okay. And then there's just some additional information here at the bottom for how I would like your figures and tables to be formatted. Okay. Okay. So that's the template. And so you don't have to write it in Microsoft Word. This is just kind of what I want you guys to have for all the different sections. So I'm not too big a stickler for the font or the font size. Of course, it should be readable. Don't use kind of a weird font in Microsoft Word that makes it hard to read. But I'm not going to mark you down if you use Calibri versus Times New Roman. Okay, any questions on the report template in terms of what's expected on there? Okay. Okay, good. Okay, and then finally, the last document I want to share with you is the rubric. Okay. So this is the grading rubric here. And so you can see that I've broken it down into each of the different sections in the template. So this kind of just makes it easy for me to grade. Okay. But I think what you guys should be able to see here is how the different sections are weighted in terms of grade. Okay. So the abstract, very small portion is only going to be worth 5 points, but a big section like the boundary conditions, that's going to be worth more. So that's up to 20 points. Okay. Okay. So discussion is another big one that's going to be worth 25 points. And just aesthetics. And so grammar, punctuation, the figures are looking clean and the report is well organized. And so there's 25 points for that as well. Okay, so overall, the entire project is worth 150. Okay. Okay, all right. And so that's everything that's provided to you. And so, the CAD files for all the different options are here as well. So CAD file for the bearing housing, CAD file for the piston rod, and CAD file for the tank. Okay. So again, first thing that you're going to do is you're going to choose a geometry and then you're going to go from there. Okay. All right. So remember, project is due Sunday, July 19th. And so, just keep that in mind. Probably I think most people will probably begin the project in earnest, probably sometime next week or maybe this weekend. Just be aware of that deadline. All right. Any final questions on the project before we kind of get back to the lecture? Okay. Okay, good. All right. So remember, if you have questions on the project, don't be afraid to Okay. All right. So let's go back to the lecture here. So let me go ahead and share my screen. Okay. All right. So back to our regularly scheduled program. Okay. All right. So before the break, we finished our discussion on the 3D element types. And so, there's, again, not too much new there. Just kind of applying the same things that we talked about yesterday with 2D element types. Okay. So now we're going to start another set of lecture notes on what I call kind of more advanced topics in meshing. Okay. So that's going to take us up until the end of the week. Okay. So we'll do that for the rest of class today. We'll probably do that for tomorrow for the first half. And then we'll do ANSYS activity 3 tomorrow as well. Okay. Okay. So the reason I call these lecture notes, I've titled them Advanced Meshing. And so if you're downloading the lecture notes and you're following along, that's kind of the title that I had for this. Okay. It's this section or these lecture notes here don't strictly follow kind of a format like my previous lecture notes. It's kind of just honestly just kind of like a hodgepodge of different meshing topics that I think are important. Some are specific to ANSYS, and so you can see kind of a lot of the settings and a lot of the metrics that we talk about here, you can look at that tomorrow in ANSYS Activity 3. But there was just kind of no better place to kind of put a lot of these topics here. Okay, so we're going to jump around a lot, and so when we switch to a different topic, it may have kind of nothing to do with the previous one, so just kind of be aware of that. Okay. Okay, so the first thing I want to do is I want to revisit the idea of mesh quality. Okay. And so, tomorrow when we do our activity, we'll actually look at the mesh quality. We'll look at the histogram of the skewness, and we'll actually look and see how that is for a typical mesh. But I do want to kind of talk about this a bit more and explain kind of a bit more in detail kind of why the mesh quality is important. Okay. All right, so just to kind of refresh your memory, and so when we refer to mesh quality, what we are really referring to is the relative shape and the quality of the shape of each of the elements themselves. Okay? So when we produce a mesh, no matter the type of geometry, and so this occurs even for the simplest of geometries. Okay, what tends to happen is that there are some elements that get produced that may have kind of a a distorted shape. It's really kind of unavoidable, and so there's no kind of perfect mesher that produces you beautiful looking elements everywhere. Okay, and the reason for that is that a lot of times when you're feeding a geometry into the mesher, it doesn't quite conform exactly to the shape of your elements, and so there's going to be always just kind of like a weird corner or a weird edge or a weird region where you kind of have to where the measure just kind of has to stuff in a few elements just to make sure that the space is filled, but those elements may not have a nice shape. All right. And so if you remember from last week, right? Ideally, all of the elements in your mesh should be equilateral in shape, right? And so that means all of the edges, all of the surfaces, all of the interior angles should be as close to equal as possible. Okay? Because what we're going to talk about soon is that equilateral elements, produce good quality solutions. Okay. But as we just kind of talked about, not every element in your mesh can be beautiful. Not every element can be equilateral in shape. Okay. And so, to kind of help quantify this or to kind of help us see or assess, the relative shape of the elements in our mesh, because any given finite element mesh is going to have the number of elements is going to be at least in the thousands if you have a decent mesh. Okay. It's practically impossible for a user to go in and examine every single element. Okay. So the way that mesh quality is quantified is that every element is assigned essentially a quality score. So the way this typically works is that, for any given finite element mesh, the software, which for us is ANSYS, but you can also do this with a bunch of other softwares as well, is that for every single element, some kind of score is computed, and then all the scores for all the elements are kind of aggregated together, and then the software can kind of report to you the statistics of all of those of all of those scores. Okay. And then based on the statistics, we can make a determination whether, on average, maybe our elements are good quality, maybe on average our elements are bad quality. And, we can even identify, maybe where the regions of the poor quality elements are, where maybe we can actually go in and kind of fix it if we think that it's affecting our solution negatively. Okay, so for example, right? So one metric for quality or one score that we can look at is the skewness of the elements. Where skewness measures how much an element deviates from its ideal equilateral shape. Right? And so skewness is a metric that can vary from 0 to 1, right? So a skewness of 0 is good. That means the element does not skew, and so it has a very nice equilateral shape. Okay. So if we just draw a triangle, right, an equilateral triangle, something like this. Okay. Right. So an element like this would have a skewness of around 0. Okay. Because that's as close to perfect or as close to perfect as I can draw. Okay. In reality, you can get a better looking triangle, but that's the best that I can do. Okay. Whereas if you had an element that was very distorted, right? So maybe one of the sides was much shorter than the others. Okay. So we have a very, very long element here that's obviously is very kind of unbalanced. This would have a very high skewness score. Okay. So when you ask ANSYS or when you ask any software to quantify and report on your mesh quality, it's going through each and every single element and computing a score of like skewness for each of those elements. Okay, which sounds expensive. It sounds like it would take a while. It's actually very cheap, right? So even if you have like 1,000,000 elements in your mesh, computing skewness is most of the time just a very simple arithmetic formula. And so basically they just look at the coordinates of the nodes and they plug it into some kind of ratio formula, and that gives you the skews. Okay, So don't be afraid to compute mesh quality. It's a very, very cheap operation. Okay. And so when you do, and so remind me tomorrow. And so I forget a lot of time, but I'll show you tomorrow how to actually do this. Okay. So there's a few different ways that the software usually reports you on mesh quality. Okay. So first of all, it tells you just the very broad statistics. And so it'll tell you what the minimum skewness is, it'll tell you what the maximum skewness is, as well as the average. Okay. So among all the elements in your mesh, it's going to compute these three quantities. Okay. Don't take these at face value, or just don't panic at looking at these values. Okay. Because a lot of times, for most meshes, like I said, most meshes, you're going to have at least one element, usually several, that just end up just being very distorted just because they're in kind of a weird spot. And so most of the time, you're going to have a max skewness of that's something greater than 0.9. Okay. So 0.9 is pretty large, right? And so that is a cause for concern. But usually it's only a few elements, right? So don't panic if you have a max skewness that's like 0.99 even, right? And so that's pretty common as well. Okay. The one to really look at here is the average. Okay. And so by the same token, the minimum also isn't that helpful because minimum is probably going to be around 0. Maybe like 0.1 or something like that. But again, don't take the max and min to heart. Because even though, in general, right, in general, a poor quality element can lead to poor solution quality. If there's only a few elements, their impact is usually pretty negligible. Okay. Because a lot of times, the locations of where you have your highly skewed elements are in areas that are usually not very consequential too. And so usually that's not too much to panic about. Okay. Now the average can be useful. Okay. And so it'll report the average to you. Okay. And then depending on the complexity of your geometry, the average skewness will probably be somewhere around 0.5 to 0.7. Okay. Right, so obviously the lower skewness is better, right? So the lower means that generally you have higher quality elements. But even if your average skewness is getting up to like 0.7, then I wouldn't panic too much about that either as well. Okay. And so the average is a bit more helpful. And so if you see that the average is very high, you know that maybe overall you need to kind of refine your mesh. Okay. Because generally speaking, as you refine your mesh, as you make your elements smaller, then it does improve the skewness. Okay. Because the general thought is that if you make your elements smaller, then they don't have to kind of distort themselves to kind of fit into those weird places. They're just kind of smaller, so they fit more naturally in there. Okay. So the average can be helpful and to look at the mesh overall, but at the same time, the average doesn't also tell you the full story either, right? Because it's not just having good quality elements overall. you really want to have kind of good quality elements in the areas where it's going to matter. Okay? And so, it's when you're talking about mesh quality, it's not just a question of, whether you have good elements overall, but, you want to make sure that in the regions where maybe you have a high amount of stress, or maybe you have, a high solution gradient, that's where you want to have your good quality elements in. All right, and so ANSYS also gives you the option to kind of help you identify where are the regions of high high skewness. Okay. Another tool or another kind of metric that, or another way that kind of ANSYS kind of shows the mesh quality to you is it also gives you a histogram. Okay. So hopefully everyone's seen a histogram before, but a histogram is essentially a bar chart. You can think of it just naively, it's just kind of a bar chart, which kind of shows you kind of how many elements have qualities in certain thresholds. Right. So the histogram will look something like this. Okay. And there will be several different buckets, right? And so maybe you'll have skewness between 0.0 and 0.1, 0.1, 0.2, 0.2, 0.3. 3, 0.4, okay, and so on. Okay. And then what ANSYS is going to show you is that you're going to see a bar chart which shows you, relatively how many elements fit into the, that, bin of mesh quality or skewness. So maybe it looks something like that. And you can actually click on the different bars in that chart there to kind of show you where those elements actually are in your mesh. And of course, that can be very useful for identifying where the poor quality elements are. Okay. Okay, so ANSYS actually has a lot of really nice tools that are actually built in. And so to kind of check your mesh quality. And so the way, before I started using ANSYS, I used a software called ParaView. And so ParaView is another software. It's an open source software for analyzing meshes and solution results. I use kind of a more manual way to check quality, but ANSYS has a lot of very nice tools to kind of do it. Okay. So remind me tomorrow. I think hopefully I'll remember tomorrow to kind of show you those tools. Okay. Which, for the activity, probably not going to be super helpful because, again, our activity geometries are pretty simple, but this might be something that you consider for your project. Okay. And speaking of the project, right? So part of the project is, like I mentioned, is, convincing your reader that your mesh is going to be high quality, right? Showing metrics like this, although not required, can be a very good way to kind of show to your reader that, you've checked the mesh quality, you checked the skewness, you checked the element shapes, and they kind of fit what they need to be. Okay. So, I'm not going to be requiring it for the project, but, definitely not a bad idea. Stuff like this. Okay, any questions on skewness and how we measure it in ANSYS? Okay, good. Okay, so that's how we measure skewness, but we haven't really talked about yet why skewness is important, right? So why is it that for an element like this, why is it that this produces a lower quality solution? And so, I've kind of just been kind of very hand wavy about it so far. So let's kind of talk about it. Okay. Okay. And so the main reason that skewed elements can produce lower quality solutions is the fact that a lot of times, kind of like we talked about yesterday with regards to shear locking, right? a lot of our equations rely on the computation of derivative-based quantities. Okay. So a derivative-based quantity would be something like the strain, right? So strain is the derivative of the displacement or the deformation, which then leads to the stress, right? And we talked about how important the stress is yesterday, because the stress is what drives the deformation in a static structure, okay? And so a skewed element will really kind of struggle to compute these, okay? The main reason is that, the way that a finite element software computes a derivative is that it utilizes a technique known as finite differences. So it sounds similar. I know they both have finite in the name, but finite differences is something that's kind of fundamentally different than finite elements. Okay, although they're used a lot. Okay? So the idea with finite differences is the following, without kind of launching into a full lecture about them. Okay, so let's say we have our element here. Right, so this is what I would consider to be a good quality element, right? So each of these sides here are roughly the same length, right? And of course, we have a linear triangle here because we only have three nodes here. Okay. Now, on an element like this, the way that we compute the derivative is that we basically take the difference between the solution at each of the nodes divided by the distance between them. Okay. That's essentially how finite difference works. And so finite difference just gives us a way to approximate a derivative. We just take the difference between two quantities and we divide by how far apart. Okay? And so if we define, right, I'm going to define the lengths of the different sides here. So I'm going to define the length on the bottom as L12. This is going to be L13, which is the length between node 1 and node 3. We have L23. Okay. Okay. We can compute three different derivative quantities related to these terms here. Okay? For example, so du dx vector, okay, can be u1 minus u2 divided by L12. Okay? Also du dx, okay, can also be u2 minus u3 divided by L23. I am kind of vastly oversimplifying this for now, and so if you've been exposed to finite differences before, I think Dr. Banks goes over finite differences in his heat transfer class, and so I know this isn't fully the finite element theory, but I just mostly just want to make a point across here. Okay. Okay, but essentially through finite differences, we can get three different measures for the derivative here. Okay, and so this would be the derivative of the quantity within that element, right? And so what we do from here, to get the overall derivative within that element, we can then take the average of these three different representations. Okay. Right, and the fact that we have a good quality element where all of the side lengths are roughly equal, right? Then we're going to get a very good average quantity because each of those, none of those is going to dominate more than the other. They're all going to contribute equally, and any differences or any kind of variation or gradients that we find is going to be purely based on the differences in the solution values in the nodal U21, U2, U3. So that's ideal, right? And so if you have a good quality element, you get good computations of derivatives within the element itself, just because all the side lengths are the same. Okay? If we compare that to a skewed element, right? So let's go ahead and look at skewed element like this. Right, and then once again, we're going to write in the lengths here. Now, with a skewed element here, our lengths are very imbalanced, right? So we have two lengths, L12 and L13, which are much larger than L23. Okay. So I'm not going to write out the full expressions for these again, right? But you can imagine that if we were to take the finite difference approximations of the derivatives, right? The derivative between 2 and 3 is going to be, uncharacteristically large or disproportionately large. Okay? And so when you go to compute the average, or when you go to compute the overall derivative for the entire element, it's going to be much more biased towards the difference between 2 and 3, which is not what you want, right? So you want kind of a good balanced derivative computation. Okay. And so if you have skewed elements, that this is kind of what tends to happen. So, your derivative-based quantities kind of get, don't get computed very accurately. And if you're doing a type of simulation or a type of physics that relies on those derivative quantities, like a structural equation, then it's going to lead to errors in your computation for deformation as well. So it's a problem that kind of cascades. Okay? But again, at the same time, right? So what we just said was that, it's inevitable that you're going to have some skewed elements in your mesh. That's just how meshing kind of works. And so if you only have a few of these elements, it usually doesn't affect your solution overall. And so the negative impact is usually pretty limited if there's only a few. Okay. That's why, usually it's a good idea to check your overall quality and just make sure that if you do have poor quality elements, there's not too many of them, and they're not all concentrated in an area which is important in your simulation. Okay. But hopefully that gives a bit more context in terms of why we want to avoid these types of elements, because otherwise your derivative computations is not going to be as accurate as it could. Okay. Any questions on this? Okay, good. All right. So besides skewness, another, or I guess maybe a way for you to kind of assess poor solution quality is to look at how the solution kind of pops around. Okay. Or excuse me. So another thing that can kind of indicate to you that a solution is poor quality is to look at how much the solution changes. Okay. So let's talk about high solution gradients. Okay. So when I talk about high solution gradients, what I mean by that is, regions where your finite element solution is going through very rapid changes. Okay, and so if your solution goes through a very rapid change, let's say very rapid change in deformation, a very rapid change in stress over a short period of time, I would consider that to be a high solution gradient. So typically, when I'm grading, finite element, results, and I do this with my grad students as well. So when I look at their simulation results, this is typically something that I look at. Okay. So high solution gradients is not necessarily a bad thing. And so a lot of times, it's just part of the physics, right? And so just based on this combination of the loading and the geometry, sometimes you just have high solution gradients. Okay. All that really tells you is that, your solution is just changing rapidly. Okay. Where this kind of gets a little bit dicey is that, you want to make sure that if you do have high solution gradients, you have enough mesh density within that region in order to capture that gradient accurately. So there should be a direct kind of correlation. So let's say that you run your simulation and you identify a region of high solution gradients. Okay. That is a prime example or kind of a prime candidate for a local mesh for fun. Okay. So just like we did with activity 1. Okay. Okay. So why is this an issue? And so this is an issue because the amount that a solution can vary within an element is limited by its shape function. So this is why, understanding the shape functions for all the different types of elements is important because it tells you, how quickly a solution can change as you go from one end of the element to the next. Okay. Okay. So, the highest order element that we can use is a quadratic element, which, quadratic is great. And so, quadratic lets you lets you vary things much more quickly than linear. But even a quadratic element has its limitations. Okay, so for instance, right? So let's even take kind of a good quality element here. Okay, so even for a relatively good quality element here, right? So let's say that we're looking at the solution going from node 1 to node 2. So basically traveling along this line. Okay. And so from our finite element simulation, let's say that we computed the solution at those two nodes, right? And so just for the sake of just illustration here, let's say that we ran a thermal simulation, and so we've computed the temperature at node 1 and node 2. So T1 and T2 are you know, are our two temperature solutions. Okay. And so even if we have a quadratic function, right? A quadratic function is we can only vary quadratically as we go from T1 to T2. And so what I mean by that, if we were to kind of plot it, right? And so if we were to make a plot that shows the variation from T1 to T2, okay? So for instance, let's say that we have a plot that looks like this, okay? And let's say that T1, T2 are very different from each other, okay? Right, so if you do have a big difference between the nodes of the element, this is what I would consider to be a high solution gradient, okay? So for a quadratic element, we're only limited to a quadratic variation, okay? And so that means, right, that the variation may only look something like that. Which, that might be what's happening, right? And so maybe the true solution is actually doing that. But we don't know for sure. And I think the and kind of the worry or kind of the concern with the high solution gradient is that, usually in a physical situation, when you have a high solution gradient like this, where you have kind of very rapid changes, very rarely does it occur in kind of a very smooth way. Okay. So in reality, right, the variation of T1 and T2 may follow a different trend. Okay. So maybe it's following something like that. So in the light blue here, this is what I would say. Maybe this is the true trend. Okay. Or maybe there's not a lot of change at first, maybe there's a lot of rapid change at the end. Okay. Which, when you look at it like this, it may not seem like that big a deal, right? So maybe our quadratic variation and our true trend, they look pretty close, okay? But remember, it's not just about computing the quality itself, right? Along the way, we're going to be computing derivative quantities as well. And so even though the computation of T1 and T2 here may not look that off, right? The computation of the derivatives between T1 and T2 are going to be, much more inaccurate if we're not able to capture that true variation. Okay. And we've already discussed kind of why derivative computations are important, because a lot of times those derivative computations feed back into your original equation. Okay. And so if there's any reason why the derivative computations are incorrect, then that's going to lead to incorrect computations of other quantities as well. Okay, so it's kind of like a negative feedback loop. And so those derivative quantities are very okay. But what we know, right? So based on kind of what we discussed last week is that if we were to add more mesh density here, right? So if we were to add more meshes in between T1 and T2, right? Then we kind of add more kind of control nodes on this plot here, right? So in the red right there, let's say that we've increased the density of the elements there, so we've added more. Right? And so by refining the mesh in these regions, by adding more elements, we're more likely to capture these very sharp solution gradients. So one thing that you're going to see is that refining the mesh is kind of the solution to every mesh related problem. And so if you're getting poor accuracy, just refine the mesh. If you're getting poor quality elements, just refine the mesh. You have high solution gradients, just refine the mesh, right? And so yes, it is true that refining the mesh will solve a lot of these problems. But remember, refining the mesh kind of gives you a different problem in that it also increases the cost of your simulation as well. Okay, so you can't just be throwing elements everywhere. Maybe in a world if we had infinite computing, we could do that. And so the key to kind of getting a good quality mesh is not just blindly just throwing elements everywhere, just refining the mesh everywhere. It's kind of being more selective in terms of where you apply your refinement. Because if you think about it in terms of like if you have a fixed budget, if you have a fixed amount of elements that you could use for your entire simulation, which is true, right? And so for those of us in this class, right, we're using an academic version of ANSYS, which does put a hard cap on the number of elements that you can use, right? And so you do have a hard cap. You do have a hard budget in terms of how many elements that you can provide. And so you want to be strategic in terms of where you're adding those, where they're going to have the most impact, okay? Because just by saying that you have a mesh of 5 million elements, doesn't really tell me anything. It's not about the raw number of elements. It's about where you're distributing them and where they're most effective. Okay. All right. Any questions on this so far? Okay. I'll give you another example, just because we're actually a bit ahead of schedule today. A very common example of where you would apply these refinements in fluid mechanics is in the area of a boundary layer. So this is kind of an aside, and so this is not strictly related to the class. It's just I thought I would just give an example from my own work. It's also kind of fitting just because I know there's quite a few people in this class that just literally just finished fluid mechanics with me just a couple weeks ago, and so this kind of is kind of a relation to kind of what we just finished talking about. Okay. All right, and so if you've taken fluids already, or even if you haven't taken fluids yet, there is this concept of a boundary layer that can occur in a flow. Okay? And so whenever you have a fluid that's flowing past a solid surface, right? So let's say you have a wind or water that's flowing past a wall that's like this, okay? There's a very thin layer of fluid that appears or that forms on top of the solid. Actually, I'm going to use a different color to make it a bit more. Okay, so this region is what we call the boundary layer. Okay, so what's unique about the boundary layer is that the velocity or the fluid velocity undergoes very rapid changes within that boundary layer. And so usually it goes from a value of 0 at the wall up to a value of the free stream, which is u infinity up here, okay? So your velocity, if you were to simulate this using a CFD code, your solution for the velocity is changing within that very small region of the boundary layer. All right, and this is pretty much universal. And so whenever you have a fluid that's contacting a solid surface, a boundary layer is always going to form. Okay. In fact, because it happens all the time, within the world of computational fluid dynamics, whether you're using finite elements or finite volumes or finite difference, you want to have a refined mesh at the region of the wall right next to or the region of the mesh right next to a solid surface. Okay. And so in fact, most CFD codes have a feature called boundary layer meshing, which is specifically designed to refine the mesh within the region of that wall. Okay. So that's just kind of one example. And so, if you've taken fluid mechanics already, hopefully you kind of remember, I know some of you may be taking fluids next semester. And so, kind of keep that in mind in the back of your head when you're talking about boundary layers. Okay. Okay. So one, very simple example kind of which occurs all the time in fluids where you want to be, you have to refine the mesh there. And so you want to kind of make sure you save enough elements in your budget to, to have a refined mesh for your boundaries. Okay. Okay, that was just kind of a quick aside, just to kind of illustrate that concept too. Okay, so one other thing that you can check, and I also check this for for the project in this class and for my students as well, is that your solutions or your contours for things like deformation and stretch should be very smooth. Okay. And so even in regions of very high solution gradient, right? If you really kind of zoom in on those regions, you should still see a very kind of smooth variation, okay? And so if I'm looking at the color contours in that area, right? And so the color kind of I would say format that ANSYS uses, it uses a rainbow kind of format, right? So things vary from deep blue to deep red, okay? Things should not jump. Your solution should not jump from deep blue to deep red within the span of an element. Okay? And so you should not have two elements next to each other like this. Okay? Where one element is deep blue and the next element is deep red. Okay? Now that's an extreme case, right? And so if I saw something like that, that's definitely a sign that you need to refine your mesh. Okay? Right? So you shouldn't see kind of a big jump like that. And so, you should see all the colors of the rainbow. That's typically what I tell students. And so you zoom in enough on, even in regions of high solution gradient, you should see, the solution transition from red to orange to yellow to green to blue. Okay. If you don't see that full variation, then there's probably something wrong. You probably need to refine the mesh. Okay. Okay, another way that this can occur is that you could have high-low oscillations between elements in a particular region, right? And so for instance, let's say we have a region that looks like this. I know this isn't a particularly good mesh just because we only have one element through the layer, but it's kind of serves our purpose here. Okay. So let's say that every other element, our solution changes. And so let's say it goes from high down to low, up to high, down to low. Okay. Right. And so if you see your solution kind of jumping around like this, so I call these kind of, rapid oscillations in the solution. Typically, this doesn't happen. Typically, you shouldn't have, your solution should hop around between values. And so that's another indication where, you probably need to refine your mesh and get, more elements in there to make sure that variation is smooth. Okay. Okay. All right. So those are just some kind of just, back of the napkin kind of just overall kind of sanity check kind of things that you can do to look at your solution results and see, whether you need to refine or not. Okay. Okay. And so, before we kind of move on, I want to talk about what I would consider to be kind of the general approach to meshing. Because usually, by the time we kind of discuss all these things, and some of you were even asking this question after activity 1, activity 2, right? How do we know, right? How do we know that the settings that we chose or the size that we chose and the order and all that stuff, how do we know that those are going to be adequate for a good solution? Okay. Well, in reality, you don't, right? And so it's very difficult, even for someone with a lot of experience, to look at a boundary value problem, to look at your simulation beforehand and tell you from the get-go, what your mesh element should be. Okay. Typically, getting a good quality mesh is an iterative process. And so usually it takes a few tries, which a lot of times, you're going to do anyway, because you're going to be doing a mesh conversions test, but you usually don't get it right the first time. Okay. So getting a good mesh is not, it's not something that you get right kind of the first time. Usually you kind of tinker with it, kind of add refinement, you take away refinement, you adjust, element sizes, element, order, element shape, until you get a satisfactory result. Okay. Okay. So generally the approach is the following. Okay. Step 1. And having a tool like ANSYS helps out a lot because you can do all of this within the graphical user interface, and it's usually very straightforward to do. Okay. So step 1 is always to generate an initial mesh. Okay. So you don't have to do anything special for the initial mesh, and so you can just go with the default setting within ANSYS itself. Okay. Just because we need to have a mesh to at least run a simulation. Oh, question from the chat. Okay, question from the chat says, when is it favorable to use a 2D mesh rather than a 3D mesh? My intuition says that most of the time we analyze a 3D part, we have to use 3D elements. Yeah. So a lot of times, whether you use 2D or 3D is going to be dependent on the dimensionality of your part itself. So if you have a 3D part, you're going to have to use 3D elements. The only reason we were able to use 2D elements on the first activity was because our plate was very thin. And so I think thickness was only like 5 millimeters compared to the length, which was, 300 millimeters. And so that thickness dimension was so small, we essentially ignored it. Not that we completely ignored it, that thickness does affect our solution. I think someone else asked about that yesterday as well. But generally, most of the parts you're going to be analyzing are 3D, and so you're going to use 3D elements for that. Okay. Now, of course, that's not an absolute statement, and so there are situations where we want to use 2D elements and even 1D elements, and so we call those special types of elements shell and beam elements. But we will talk about those early next week on Tuesday. And so there are situations where we can change, but yeah, it has to be within a certain special case. Okay. All right, so step one, generate your initial mesh, and then from there you can apply your boundary conditions. Okay. These are just kind of the basic, basic steps to running a simulation. I guess even before this, you would assign your material properties as well. So I don't want to make it seem like I'm forgetting that. Okay. Let's write that in actually. So step three, assign material properties. We want to make sure we don't forget that. That is actually the step that most people forget, is they forget about the material properties. Okay. Next is just to run a simulation. Okay. And remember, we're only running with the initial mesh right now. So, we're kind of conceding the fact that, maybe our solution isn't as accurate or reliable as it could be. Okay, but we do need to run a simulation because otherwise we wouldn't be able to assess the mesh. Okay. Okay, and then step 5, once we have our simulation results, then we can start to go in and we can check and see where are the regions of high solution gradients, where the regions where our solution is oscillating. Okay. Next is identify regions mesh improvement. So some things we can check are high solution gradients. Next thing we can often check is areas of stress concentration. Usually areas of stress concentration also correlate with areas of high solution gradients as well, because if you have a very high stress, usually it's only in a very localized region. Okay. We can also look at mesh quality for skewness. Okay. Which again, remember, by itself, skewness isn't necessarily a bad thing, but if you have highly skewed elements in a region where you have high solution gradients, that's usually kind of a good indication you need to refine the mesh thing. Okay. Etc. Okay, and then once you've identified those regions of mesh improvement is to actually go in and refine the mesh. Also keeping in mind the overall number of elements and your mesh element budget. Okay. 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 On the flip side, you could also look for regions or look for areas where maybe we can actually coarsen the mesh, right? So maybe there are regions of your solution where, maybe not much is going on. There's not really much interesting going on there. And so we can actually, reduce the size or reduce the number of elements so that we have more elements to use in other areas as well. sometimes that makes a difference. And so sometimes, you'll have a region where, you look at it and say, hey, maybe I don't need that many elements in that area. Maybe I can take those elements and put them somewhere else. Okay. Okay, and so after you make the modifications for your mesh, you're going to run your simulation again. Okay, and then from there, you're just going to repeat, right? And so you're going to repeat this process until you're, basically satisfied with your mesh. Okay. And eventually, you're going to reach a state of mesh convergence, which, probably we won't have time to talk about today. Or maybe we will. Maybe that'll be the last thing that we talk about today. Yeah, let's do that. So let's talk about mesh convergence today, and then we'll talk about the rest of the topics tomorrow. I think that'll be good enough. I think mesh convergence is kind of a very fitting topic. It's a nice topic we can talk about for just the last 10 minutes before we head out. Okay. All right, but in general, this is kind of the process, or this is kind of the procedure for generating a finite element mesh. Okay, so again, it's not something that you identify and you do on the first step. Usually there's several steps that you have to do in order to get there. Okay. All right, any questions on this procedure here? Okay. All right. So last topic that I want to cover for today, just to kind of, as it's kind of a fitting conclusion to this, is this idea of mesh convergence. Okay. So hopefully this kind of closes the loop in terms of all these kind of meshing topics that we've been discussing. Okay. All right. So if you look at the word convergence by itself, convergence basically means when you come together on a certain region, okay, or certain topic or certain kind of agreement. Okay. Mesh convergence basically means that mesh convergence is a point where if we were to try to refine the mesh any further, we would not achieve any differences in the result. Okay. And so if you've achieved mesh convergence, that means that if you refine the mesh any further, and so if you made the elements any smaller, or if you you added more refinement, right? You don't really get any benefit from it. Okay, so the solution doesn't really change. Okay? Think back to the statement that or kind of the definition that we looked at last week for what makes a good mesh, right? So remember when we first introduced the idea of meshing, a good mesh is one that gives you an accurate solution for the least amount of cost. Okay, we can define that a little bit more precisely now, and so a good mesh is one that reaches mesh convergence, where if we refine the mesh any further, right? So if we incur any further costs, then we don't actually get any improvement on the accuracy. Okay. Now you could make the argument, you could say that if you achieve mesh convergence, then we're converging on the true solution of the differential equations. Okay. And a lot of times that is the case, right? And so when you do converge, a lot of times you're converging on what the true solution is. But there are other factors that kind of mess that up as well. So there could be like singularities and stuff that could occur. Okay. But kind of the raw definition of mesh convergence is that you reach a state where if you were to refine the mesh, if you were to add more elements or make the elements smaller, you just don't get any benefit from it. Okay. Now it gets this name because a lot of times, or I would say every time when you run a finite element simulation, you want to conduct what's called a mesh convergence test. So a mesh convergence test is something that you can do to kind of show that your mesh is converged. And most of the time, this is a requirement for you to include in any kind of technical report where you report any kind of computational results. Okay. Now, I'm not requiring a mesh convergence test for the midterm project, but for the final project, I am going to require. Okay. So the idea with the mesh convergence tests is that you're going to run several simulations with each time you run the simulation, you're going to refine the mesh more and more. And so you can do this as naively as just altering just the global mesh size just to increase the number of elements. Okay. And then what you're going to do is that each time you run a simulation, you're going to write down or you're going to record the value of a key solution metric. And so examples of a key solution output, usually for structural simulation, you're going to want to record the stress. Okay. You can also do this with deformation technically as well. Okay. And then what you're going to do, so after you run all of these simulations and you record the key solution output, okay, you're going to put all of these onto a single plot called your mesh convergence plot. Okay. Okay. So usually it's a scatter plot that looks like the following. So on the vertical axis, you're gonna put down your recorded output value. Okay, so let's say that we are recording the stress. And then on the horizontal axis, we're gonna input some kind of metric that defines the refinement of the mesh itself. Okay. So there's different ways to do this. The way that I typically like to do it is I like to record the total number of elements in the mesh. And so for each of the simulations that you ran, you're going to record a data point for each of those, right? So let's say for your initial mesh, right? So your initial mesh has a relatively low number of elements, right? That will be your first data point. And then each mesh that you refine, right? You're going to record more and more data points. And then you should be able to connect them all with a line. Okay. And what you should see is that eventually, right, if everything goes according to plan, you're going to reach a point where this plot is going to plateau. Okay. So I would say that occurs probably around right here. Okay. And so you can see that once we kind of pass that point of convergence, right, we're increasing the number of elements. And so we're increasing the cost, but our solution value is not changing, right? And so we're paying more computational resources, we're paying more time without really any benefit. And so our solution has kind of reached peak accuracy at this point, okay? And so what we can say is that this mesh right here, the point of convergence, that's kind of the perfect mesh to run for our simulation, okay? And with this, that you can improve, you can show and you can kind of demonstrate in your report that further refinement is not going to improve your solution because you've reached convergence, okay? So that's the point of where you know you should stop with your mesh. Okay. All right, any questions on this? Okay, all right, so that's all the time we have for today. And so I will go ahead and post this up tomorrow morning. And so when we come back tomorrow, we have ANSYS Activity 3 and the rest of these lecture notes today, okay? And so thank you guys for coming today. Hope you guys have a good rest of your evening, and I will see you all tomorrow. Thanks, guys. Sure. Okay.
Is there something to fill out for this class so we can help?
Yeah, so there is because you do have to do the additional graduate assignment. Can you send me an email and I can email you the form.
Also, they have a question.
Sure.
Have a good night.
Sure what that means.
The numbers.
Yeah.
Oh, so the nodes are just just because you know the shape is defined by the nodes, and so every element has nodes that kind of. And so, if we were to go deeper into the finite element theory, what we would find out is that the solution, when we actually save the solution and we actually save it into the computer, we actually save it at the locations of those nodes. But for our purposes, you can think of the nodes as just defining the shape of the geometry. Okay, so if the nodes were kind of shifted, and so if we were to make kind of a skewed element, those would be kind of closer together.
Okay. And skewing is that.
So skewing is bad mostly just because of how it computes the derivative. And so, so when we compute the derivatives, right, when we have a skewed element, then these lengths in between the different nodes are imbalanced. And so you have one that may be really short or maybe one that's really long. And so when you compute overall derivatives, right, it's because the lengths are uneven, then you're not going to get an accurate computation of the derivative.
And we can fix that by refining our mesh, right?
Exactly.
Like we did for the first assignment?
Exactly. Yeah. So you refine your mesh. And so usually an element like this occurs because you have kind of a weird region in your geometry where you can't really fit an element in there. So you kind of has to stretch. But if you refine the elements there, then you can imagine if you try to fill that space with 5 different elements, then those 5 in that same space, they're going to be much more closer to that shape.
Okay. For the midterm, for example, like what are there different types of refinements? Well, I think we talked about it too.
Yeah, so you can do, usually when I talk refinements, practically you're going to be doing like an H level refinement, which just means just making the elements smaller in a particular region.
Okay.
Technically, there's P level refinement too, but like I mentioned, for the most of the time, if you're using ANSYS, quadratic is the way to go, just because there's really no reason not to use quadratic because just make it so easy to
do that. Especially like because I know you said I remember asking like for an example, and you said like we're obviously not using a cluster, right?
Mm-hmm. Yes,
80% of it, so might as well just do quadratic.
Exactly.
Okay. Yeah. Okay, yeah, I'm just making sure that I know what I'm seeing because it was a 5-week class.
Yeah, no, for sure. Yeah, no, you got to stay on top of it.
I was like looking over my notes and I was like, what I'm reading right now.
Yeah, no, it's good. I mean, yeah, ask questions for sure. Because once we get to next week, like next week is like a whole month in a regular semester. So yeah, you don't want to you want to make sure you get everything answered for sure.
Okay, then I'll send you an email. Yeah, I appreciate it, Professor.
Yeah.
We'll see you soon.